The next speaker is Dr. Anderegg from Harvard. And Dr. Anderegg received his bachelor degree from Berkeley and PhD from Harvard, where he worked on laser cooling and trapping of molecules. And he's continued working on laser cooling of molecules as a Harvard Quantum Initiative postdoc, and is currently a research associate in the group of John Doyle. Can you hear us, Loïc?
Thank you. Thank you for the introduction. So today I'll talk to you about our work of laser cooling and trapping ultracold molecules and using these molecules for a wide range of quantum science applications. So let me begin in this talk as a brief overview. I'd first like to introduce why we're interested in ultracold molecules and a bit about their applications. And then I'll talk to you about some recent progress on implementing basically molecular qubits. And then finally wrap up with some new molecules we're exploring for new platforms and new ideas. So why are we interested in ultracold molecules? So this is due to the really kind of the three main kind of applications of ultracold molecules. They can be used for quantum simulation and quantum computing. They can be used for studying quantum chemistry and ultracold collisions. And finally, they can be also used for quantum sensing and precision measurement applications. But today in this talk, I'd really like to just focus on the first in this section and really just focus on quantum simulation, quantum computation of ultracold molecules. So when I say quantum simulation and quantum computation, what exactly do I mean? So this can really be kind of broken down into the fact that quantum simulation is basically analog quantum computation, and then you also have digital quantum computation. So what do we mean by analog quantum computation or quantum simulation? The basic idea is that you're trying to basically solve the dynamics, for example, of some Hamiltonian. So an example that's often given for this is, for example, say you want to study the dynamics of a real world system, maybe, for example, like this high temperature superconductor shown here. You can model the strongly correlated electron system as, for example, a set of electrons within some crystal lattice. And you can even write down a Hamiltonian for this system. But if you try to solve this directly, this turns out to be very computationally difficult. So instead, the idea is to then basically simulate this Hamiltonian within some other quantum system. And this has been done quite successfully with a wide range of platforms, for example, of trapped ions, ultracold atoms, superconducting qubits, as well as ultracold molecules. The counter-side to this quantum simulation idea is really digital quantum computing, where here the idea is basically you want to basically engineer some quantum circuit with a set of quantum gates. So this is maybe more similar to what you think of how, for example, your everyday computer works. Now, there's a wide range of various platforms that have really been introduced over the past several decades to tackle these problems. For example, superconducting circuits, trapped ions, photonic qubits, quantum dots, color centers, as you just heard, and also neutral atoms. And today I really want to just focus on this neutral atom approach because it's very similar to what we're also working on. So these neutral atom quantum computers, the way they work is by using what's known as optical tweezers. And the idea of optical tweezers is basically you have these very tightly focused optical beams, and they're so tightly focused that each one of these beams is able to load a single atom or a single molecule in our case. You can then rearrange these very tightly focused tweezer traps in arbitrary dimensions and geometries, whether it be in 1D, 2D, or even 3D. And it's really this programmability and controllability that this platform affords that gives it its strength. And with this platform, for example, people working with ultracold atoms and specifically exciting ultracold atoms to Rydberg states have been able to use this for a wide range of quantum simulations, as well as showing quite promising results for quantum computing, as well as some quantum metrology applications. Now, why would we want to do this with molecules rather than atoms? And there's a few reasons for this. So molecules have a strong and tunable long-range interaction. And this long-range interaction really has to do with the fact that molecules have electric dipole moments. And it's this electric dipole moment that we use to really couple the molecules together and entangle them. They also have a wide range of internal level structures, and this means they can be controlled and manipulated with a wide range of optical fields, RF fields, and microwave fields, for example. And finally, they also have very long coherence times. And the fundamental reason for this is the fact that molecules have this long-range interaction within the ground state of these molecules. So rather than being, for example, some short-lived metastable state, because you're in the ground state, this kind of naturally gives you this long coherence times. And finally, just like ultracold atoms, all ultracold molecules are, of course, quantum mechanically identical, which means that, of course, this allows you to be quite easily scalable to large system sizes. And because of basically all of these advantages, there's been a lot of theoretical work over the past several decades that have looked into implementing a wide range of quantum simulations with ultracold molecules. And here's just a short list of some of the problems that have been theoretically proposed that could be solved with a quantum simulator made of ultracold molecules. The same properties that make molecules very useful for quantum simulation will also make them very attractive candidates for quantum computation. And specifically, people have looked at, for example, loading ultracold molecules into tweezer arrays and found that with fairly reasonable experimental parameters that we hopefully can achieve in the next few years, we should be able to reach gate fidelities of up to 4 nines of fidelity. Additionally, molecules, because of their rich internal level structure, could also be used not just as qubits, but as qdits, basically making use of this higher dimensional Hilbert space that you have available. And finally, they've also been shown to be quite useful for a wide range of quantum error correction protocols. The last question I want to answer is, why do we need these molecules to be ultracold? And this has a few answers. First of all, we need the molecules to occupy a single quantum state. So at room temperatures, molecules will occupy thousands, millions, or even billions of internal states, depending on the molecular complexity. And really cooling them collapses this internal state distribution into basically a single quantum state. Additionally, as we cool the molecules down, we also are able to reduce any sort of Doppler shifts and narrow spectroscopic lines. So this gives us then increased resolution. And finally, going to ultracold temperatures also allows us to increase the interrogation times. So this will further increase, for example, the resolutions we're able to achieve. And it also gives us the ability to trap molecules. And this ability to trap molecules is what we use, for example, to load these molecules with single particle control into these optical tweezer arrays. So maybe to summarize, going to ultracold really gives you two things. It gives you quantum control of your molecules, and it gives you low decoherence rates. So how do we actually go about producing ultracold molecules? And there's basically been two different approaches to this problem over the past several decades. One is via assembly, basically assembling molecules from ultracold atoms. And the other way has been direct cooling methods. And that's what I'd like to talk to you about today, specifically focusing on laser cooling of ultracold molecules. And this laser cooling of ultracold molecules has a few nice advantages. Mainly, we have access to really all of the laser cooling techniques that have been developed over the past several decades for ultracold atoms, and we can now apply these to these molecules. This also allows us, for example, to non-destructively image and detect our molecules. And you'll see that this method is actually not just limited to a few molecular species, but actually to a wide range of molecular species, including more complex polyatomic molecules. Now, of course, laser cooling of molecules turns out to be quite challenging. And this is the basic reason with the fact that when you want to laser cool, for example, an atom, what you do is you excite the atom to some excited state, and then the atom will decay back down. And each time you do this, you get an h bar k of momentum kick to slow down your molecules and or atoms and cool them down. When you try to apply this to a molecule, however, most of the time, rather than the molecule decaying back to the state you started in, it will end up in another of its internal state. And because there's so many different internal states, if you don't have some way of controlling all of these decays, you would basically need an infinite amount of basically lasers to address all of these transitions. So let's look a bit more carefully at kind of the molecular structure and how we actually go about laser cooling a molecule. So basically, there's 2 degrees of freedom we need to talk about. The first is the rotational degree of freedom. Thankfully, there are selection rules that we can make use of here. And this means that we can basically cycle photons from the n=1 ground state to the n=1 excited state. And because of this delta n=1 selection rule that arises from parity, the molecules will always decay back to the n=1 state. And this allows us to be rotation closed and not worry about decays to other rotational states. As far as vibrational states are concerned, unfortunately, there are no selection rules. And here instead, we're making use of basically selecting the right type of molecule. So it turns out there's actually a wide class of molecules that support laser cooling. And there's kind of a diagram here showing what type of molecules these are. So these are basically some sort of metal attached to a ligand. And because of the bonding process and because of orbital hybridization, what happens is that when this bonds, you'll see that the electronic wave function actually gets localized around the metal atom and gets pushed away from the molecular bond. So this basically kind of decouples the electronic structure from that of the molecular excitation. And it means that this molecule turns out to be almost atom-like when it comes to the laser cooling process. And as a result, then, when it comes to laser cooling, we now have a structure that looks something like this, where the probability of decaying to higher lying vibrational states becomes very quickly suppressed. And this is just a quick picture showing you that in the molecule we use, calcium fluoride, this is indeed the case. So if you look at the electronic wave function, you see that the electronic wave function is really localized around the metal and not so much around the molecular bond. Now, of course, this idea can hold also if we simply replace this ligand with something more complex, or maybe something even more complex. And you can see even with this very complex molecule shown here to the right, that this still holds. And even a molecule like this can then be laser cooled. So how do we actually go about producing these molecules and laser cooling them? Well, this is a brief overview of how we do this. We first begin by producing the molecules in a cryogenic source and cryogenically cooling them with collisions with cold helium gas down to a few degrees Kelvin. At that point, we apply a counterpropagating slowing them to load them into something known as a magneto-optical trap. This is basically kind of a workhorse technique in all modern AMO experiments that really combine magnetic fields with optical fields to give you simultaneous trapping and cooling of your atoms or molecules. We can then apply further laser cooling to reach subdoppler temperatures, and then finally load them into optical dipole traps. Once we're able to cool them and load them into optical dipole traps, we're then able to load them into these tightly focused optical tweezer arrays, as shown here. And you can see, for example, a histogram of one of these optical tweezer arrays showing that we can very well characterize whether we have a single molecule loaded or no molecules in any individual tweezer trap. With this, we can then, for example, also rearrange these optical tweezer arrays into defect-free arrays. And we can also, have, for example, have site-resolved addressing, really talking to a single individual molecule within this array, while leaving, for example, the neighboring molecule untouched. We can also have basically full coherent quantum control of these molecules with a combination of optical pulses and microwave pulses. You can see we can drive some nice Rabi oscillations between various internal states within these molecules that are trapped in these tweezers. Now, how do we actually go from this platform into achieving some sort of molecular qubit? So to achieve some molecular qubit, we basically need a few things. We, of course, need the ability to address and detect individual molecules. And this is kind of given to us naturally, as I just showed to you with this tweezer platform. But we also need, of course, long coherence times. And we need some way of entangling the molecules together. And finally, you'll see that we'll also need some way of suppressing some thermal dephasing that we see. So let's dive into a bit more details in each one of these topics. So let's begin by looking at how do we achieve long coherence times. So to kind of understand what gives you these long coherence times in these tweezer traps and what can limit you, we can first look at, for example, the role of the AC Stark shift. So the AC Stark shift is, of course, what we use to trap these molecules in these tightly focused tweezer traps. But it also has a problem, which is the following. If, for example, your two qubit states have different sensitivities to your trapping light, this means then if you have a change in the intensity of your trapping laser, this will cause a shift in your qubit transition. And this will, of course, lead to dephasing. The same idea is also true if any of your transitions are either sensitive to magnetic fields or electric fields. Any change in the ambient magnetic field or electric field within the lab would also cause dephasing. So here, really, the goal is to find a set of qubit states within these molecules that basically have minimal sensitivities to all three of these. And that's what we've been able to do. So by basically tuning the polarization angle of this tweezer trap in combination with some magnetic fields, we're able to basically tune the derivative of this light shift to basically have a zero derivative. And this means then we're minimally sensitive to any change or any noise in the trapping intensity. And this allows us to then get much longer coherence times. How long are these coherence times? So you can see this in the center plot here. So for simple Ramsey coherence times, we get about 100 millisecond coherence times. And with a single spin echo, we can push this up to half a second. And with higher order dynamical decoupling pulses, we can push this out to over a second or even several seconds. And I also want to make the point that this rotational coherence time is within various qubit states. So these are not storage states. These are actual interacting qubit states. The other thing that's kind of interesting is the fact that if you look at this coherence time versus the temperature we have, you can see that it basically scales linearly. So this means that in the future, if we're able to further cool these molecules down, we'll be able to achieve even longer coherence times. Nevertheless, the coherence times we achieve are already significantly longer than the predicted gate times. So in essence, we've already created here a useful qubit. So with this, we can then bring in two of these molecules close to one another, and we can then observe dipolar interactions between the neighboring molecules. So what you see here is basically spin exchange due to the dipole-dipole interactions between these neighboring molecules as a function of distance. What you might also notice is that while there is this interaction, you'll see that this also dephases much quicker when the molecules are close together than when they're further apart. And the reason for this really has to do with the fact that the molecules still have some finite temperature. And this finite temperature means that the molecules can actually move around in the axial direction of these tweezer traps, and this changes the relative distance between the neighboring molecules as a function of time. And this is what causes this dephasing. Nevertheless, we can already make use of this dipolar interaction to then create a set of entangled states. So here we've created, for example, a Bell state, and we achieve a Bell state fidelity of about 90% or so. So this is, we believe, a quite good start to using kind of molecules as a new qubit platform. And I just want to put this kind of on this plot that kind of shows all the various qubit platforms that have come up over the past several years. And I just want to point out that molecules are really a newcomer to this. So we've only kind of achieved single particle control over the past few years, but we hope to make, again, very rapid progress, improving the qubit gate fidelities that we can achieve. Now, of course, we'd like to do better. And of course, the first step to this is to get colder and remove this thermal dephasing. So of course, how can we do that? Well, the one way to do this is by using something known as Raman sideband cooling. And this is basically a technique to basically cool the motional degree of freedom within these tweezer traps down to the ground motional state. So this is basically done with a two-step process. The first is to drive a Raman transition between basically one quanta of motion to one less quanta of motion. And then you apply an optical pumping pulse, which brings you back to this upper manifold. And then you simply repeat this process over and over again until you reach the ground motional states of these tweezer traps. There are some complications if we want to apply this to molecules rather than atoms. But thankfully, much of the theory of how this could be done was first worked out by the group of Mike Tarbot, and we've simply basically followed this theory proposal. There are some additional complications, which is the fact that we're actually so hot that we occupy many, many modes. So just to give you some sense, axially, we occupy over 40 modes within these tweezer traps. This means we're actually well outside what's known as the Lamb-Dickey regime, which means we actually need to start applying higher order, basically cooling pulses as we cool them down to make sure that we really transfer all the population down to the ground state. When we do this, this actually works quite well. And we reach a final, basically, average occupation on both the axial and radial direction of n bar of about 0.2. Or you can think of this also as we reach the full 3D ground state of about a 55% chance. So now that we've kind of fixed this thermal dephasing issue, of course, we'd like to go back and try to improve the qubit gate fidelities that we have achieved. And also in the future, kind of try to push this even further with, for example, optimized pulse sequences, exploring these molecules not just as qubits, but as qdits, and also exploring various ways of further increasing the interaction rates. Now, what if we want to move beyond the diatomic molecule, beyond calcium fluoride? There's a few reasons you might want to do this, and I think it's well summarized actually by this figure here. And it's a basic idea that as you add complexity to your system, you also add new opportunities and new possibilities. Whether it be for quantum simulation, as is shown here, or for example, also using these as qubits or new ideas for quantum error correction. Additionally, as we go beyond diatomic molecules to polyatomic molecules, we also gain the fact that these polyatomic molecules now have angular momentum around the internuclear axis. And this leads to, quite generically, to what's known as parity doublets. And it's these parity doublets that we use basically as our science states for all of these applications. It also means that because these parity doublets are closely spaced, we're able to very easily polarize these molecules fully at very low electric fields compared to diatomic molecules. You can also see that these molecules can be fully polarized, which means, again, this will reduce the kind of the sensitivity we have to any change or any noise in the electric field that we apply. The molecule we've been working with over the past few years to achieve this is CaOH. So now there's a few additional degrees of freedom from just the vibrational degree of freedom I talked about earlier. And basically, this vibrational degree of freedom gets replaced with these stretching modes, as well as now you also have this bending mode you can think of as the molecule bends. And you have some hybrid mode of a combination of the molecule bending and some stretching going on. So these are kind of all the decays we need to kind of deal with in order to laser cool this molecule. So we apply about a dozen lasers, which repump all of these various transitions. And this then allows us to cycle over 10,000 photons, which is enough to do, again, all the laser cooling and trapping I mentioned earlier. So with this, we've been able to load these again into these magneto-optical traps with tens of thousands of molecules, cool them to subdoppler temperatures, and then load them into an optical dipole trap. One thing I want to talk about very briefly is the fact that many of these molecule experiments have been limited in the past due to basically the limited number of molecules we're able to trap in these optical dipole traps. And you can see there's actually quite a wide gap between the molecules we have in this magneto-optical trap and this optical dipole trap. And the reason being really has to do with the fact that these magneto-optical traps have quite low densities. So we've spent some time recently trying to improve this. So let me first try to explain what the current problem is with these existing magneto-optical traps. And this has to do with the fact that we have subdoppler forces that are kind of at work here. So if you look at kind of the level structure that we have when we do laser cooling, we see that we have both these dark states as well as these bright states. And these bright states are AC stock shifted by the cooling light we're applying. What happens is that the molecule, as it moves along, will motionally couple into this bright state and then fall down this potential hill. When it falls down the hill, it gains energy, and then it gets excited back up to this dark state. And this process repeats over and over again. So this is basically a Sisyphus-like heating mechanism. And if you kind of look at then what's happening in this magneto-optical trap, while the magneto-optical trap works with this Doppler cooling typically, this Sisyphus-like heating effect really decreases the densities we're able to achieve. And you can see this quite clearly experimentally, that as we ramp down the intensity of our trapping light or cooling light, you see that the temperatures reduce and the size of the magneto-optical trap also reduces. Now, this brings about, of course, some ideas of how can we fix this. And one of these ideas is to switch to a blue detuned magneto-optical trap. And this will then switch basically the Sisyphus heating feature into a cooling feature. So this idea was actually first proposed again by Mike Tarbet's group a few years ago and recently demonstrated in some diatomic systems. So we spent some time trying to apply this to a polyatomic molecule like CaOH. And kind of the first thing you could do naively is just switch the detuning of our laser beams within this magneto-optical trap. But because this is a quite complex systems, we actually spent some time to make basically a full 3D Monte Carlo simulation. And in doing so, we actually discovered something quite interesting, which is the fact that if we add this third frequency up here closely detuned to this other one, we see we greatly increase the trapping forces available to us. And we see that turns out that when we implement this experimentally, this also turns out to be the case. And you can see a dramatic increase in the density here. So this is about 20 times dimmer than, 20 times more dense than this initial 3-frequency blue MOT. And it's about 3 orders of magnitude denser than the initial red detuned magneto-optical trap. And it turns out this actually turns out to be the densest magneto-optical trap to date, even though this is a quite complex polyatomic molecule. You might wonder what's going on with this third frequency. Why does this work? So the basic idea is that this third frequency basically interferes with the other frequencies we have, and it creates basically a lattice potential. Because there's 2 frequencies, this lattice potential basically has a difference in frequency, and this causes this lattice to move with one polarization to the left and one polarization to the right. And what happens basically is we laser cool the molecules into the moving frame of this lattice. They're then shuttled to the center of the magneto-optical trap and dropped off. You can also see this in terms of velocity, that the molecules actually initially accelerated into this lattice velocity and then dropped off in the center of the magneto-optical trap. And you can also see this in this toy simulation here, that as the molecules are really compressed in this blue detuned magneto-optical trap, you can see that they're initially accelerated up to the lattice velocity before being dropped off in the center of the trap. So with these now higher density optical dipole traps, we've also been able to study a few other things. We've studied really the coherence times or the lifetimes we have available to us within these science states. We've again been able to kind of reproduce the full quantum controls that we had with diatomic molecules, but on these polyatomic molecules. And more recently, we've also studied collisions, and we're also trying to study shielding effects within these polyatomic molecules. In the final few minutes here, I just want to talk about using these molecules more in the pathway of qubits again. So one thing we, of course, want again is long coherence times. And we can actually, for example, make use of some of the nice feature of the polyatomic molecule structure to tune basically the G factor of a specific state to 0. So this just means we're tuning basically the magnetic field sensitivity of this state to have a 0 crossing. And when we do this, we then see that we dramatically are able to increase the coherence times available to us. So basically, any sort of ambient magnetic noise would typically cause dephasing. And when we approach this 0 G factor state, you can see that we dramatically increase the coherence times that we have available. Finally, the last kind of step that we want to do, of course, is to also load these more complex polyatomic molecules into optical tweezer arrays. So I've also already told you how we can do this for diatomic molecules, but can we now apply this to polyatomic molecules, or is there something that we run into that limits us? So I just want to talk very briefly about kind of one thing we've discovered in trying to do this. which is the fact that when we initially searched for these optical tweezer rays, our histograms looked something like this. So this is, of course, very different than the histograms I showed you earlier that very clearly distinguished one molecule from 0 molecules. And here you can see that something's clearly not going well. And basically what happened here can be shown in this image over here. So these are all of the laser cooling transitions I mentioned earlier. What I did not show you are all of these high-lying states. And what happens is that when we turn on the tweezer trapping light, we couple all of these excited states to all of these other excited states. And it turns out that this is quite a large mess of states that really shift the resonance frequencies of all of these various laser transitions all over the place. So we spent some time really characterizing the shifts of each of these individual states to really understand what was going on. And once we were able to do this, we're then basically able to tune the trapping wavelengths to specific wavelengths to avoid all of these features. And when we do this, we can then re-achieve these optical tweezer rays, but now for these polyatomic molecules. So again, you can see an average image of this optical tweezer ray system, as well as single-shot image showing single individual polyatomic molecules trapped, as well as the histogram here. Finally, we've also been able to basically regain all of the single quantum state control we had for diatomic molecules, as well as the coherent manipulation of these polyatomic molecules within these tweezer traps. So with that, I'd like to conclude by saying that hopefully I've convinced you that molecules, both diatomic and polyatomic molecules, have a wide range of applications for quantum simulation, quantum information, as well as also fundamental physics and quantum chemistry. And with that, I'd like to thank all the many people involved in all of these experiments, and thank you for your attention.
Thank you, Dr. Anderegg. If there are any questions, since we are already 20 minutes after the planned schedule, you could put the questions in the Q&A, and we can move on to the next speaker. Jason, yeah. Thank you. You want to?